An earthquake that you feel but don't see. Deep underground, the plates that make up the Earth's crust are moving around. Sometimes they bump into each other at their boundaries. Because the edges of the plates aren't smooth, they can't just slide past one another. So when they bump into each other, the edges get stuck, but the rest of the plate continues to move. Eventually, the rock in the location where the plates are stuck breaks and releases a large amount of built-up energy. As a result, the ground shakes violently and we have an earthquake. This is much like you pushing on an object that is lodged in place. You can push and push to get it moving, and if you eventually push enough, it will break free, but you might want to make sure you don't go toppling over when it releases. Scientists can learn a lot about earthquakes by studying seismic activity, which is the frequency, size, and type of earthquakes an area experiences over time. Since earthquakes happen deep underground, seismic activity can't be measured where the earthquake actually occurs. Instead, it's measured using an instrument called a seismograph, which records ground shaking activity caused by earthquakes. The recording made by the seismograph is called a seismogram. Just like dropping a stone into a pond sends water waves out in all directions from the center, an earthquake also sends waves out in all directions from its center through the land, called seismic waves. An earthquake has different types of waves that it sends out. The first type of waves that travel through the ground during an earthquake are called body waves, which are waves that travel through the Earth's inner layers. There are two types of body waves, P and S waves. P stands for primary, S for secondary. In order to understand how body waves move through the ground, we're going to compare them with the movement of a slinky. If you take a slinky and sort of shimmy it back and forth, a wave travels the length of the slinky, but the slinky appears to stay in one place. This is called a compressional wave because the wave compresses the medium it's traveling through as it moves along. P waves travel in this fashion. S waves move a bit differently. Take our slinky again. This time, hold both ends, but now move one end up and down like a whip. A wave travels down the length of the slinky, but more like a wave over the surface of water. This up and down wave movement is called a transverse wave. Primary and secondary waves are named as such because of how fast they travel. P waves are the fastest seismic waves, and secondary waves are the second fastest. Think of these like thunder and lightning. Light travels faster than sound, so you see the lightning before you hear the thunder, even though they come from the same source. Body waves are the same. P waves arrive first at the seismograph, the primary wave to arrive, followed by S waves, the second wave to arrive. Just like scientists know how far away a lightning strike was by measuring the time until the thunderclap, scientists can determine how far away an earthquake is by measuring how much later S waves come than P waves. The other type of waves produced by earthquakes are surface waves. These are waves that move across the surface of the Earth, and because of this are the waves that cause the most damage. The two surface waves are love waves and Rayleigh waves. Love waves are the fastest surface wave, still not faster than P waves though, so you can think of them as loving to travel across the ground. These move in a snake-like fashion, moving from side to side. It's like a transverse wave, flipped on its side, moving the ground horizontally. Rayleigh waves roll across the surface of the Earth much like an S wave does underground, or like a wave rolls across the surface of the ocean. The ground moves up and down with the wave movement, which, as you can imagine, does quite a bit of damage. In fact, most of the shaking that is felt during an earthquake comes from Rayleigh waves. While these different types of wave can't help scientists predict when an earthquake will occur, they can provide a lot of information about an earthquake after the fact. Remember our seismogram? It's created with a pen that moves correspondingly with the ground shaking. And not only does it help to pinpoint the exact location an earthquake occurred underground, but it can also tell us about the size of an earthquake or its magnitude. The larger the squiggly lines, the greater the magnitude of the earthquake. By studying this seismic activity and comparing earthquakes over time, scientists can better understand where earthquakes occur most often and why. We know that most earthquakes occur along plate boundaries, but some boundaries seem to produce more earthquakes than others. If we can look back into history to see when and where earthquakes occur, as well as how strong they were, cities that are more prone to this type of natural disaster can better prepare for future ones. Seismic activity is what scientists use to study earthquakes and identify their origin. This is the frequency, size, and type of earthquakes an area experiences over time. By studying when, where, and how strong earthquakes were in the past, we may be better able to understand future ones. Though earthquakes can't be predicted, they can be measured as they are occurring. Earthquakes come from rock breaking deep underground, so an instrument called a seismograph is used to measure the ground shaking produced. The recording made by the seismograph is called a seismogram. A seismogram looks like a bunch of squiggly lines, similar to a polygraph test, and the size and length of the lines relates to the magnitude or how strong the earthquake is. The ground shakes because an earthquake sends out waves from its center, just like waves get sent through a pond when you drop a rock into it. The waves move the land up and down and side to side and are used not only to determine how strong an earthquake is, but also where it originated. Body waves, which are seismic waves that travel through the Earth's inner layers, move at different speeds. Primary waves, P waves for short, travel the fastest and are the first, or primary waves, to register on a seismograph. These compressional waves travel through ground by compressing it as it goes, much like a slinky gets compressed if you shimmy it back and forth. Secondary waves, S waves for short, are the second waves to reach a seismograph. These are transverse waves which travel up and down like the slinky would if you whipped it vertically. By knowing how much faster P waves travel than S waves, scientists can calculate the distance of the earthquake, much like calculating how far a lightning strike is by measuring the time until the thunderclap. Surface waves are seismic waves that travel across the Earth's surface. While these travel more slowly than body waves, they tend to cause the most damage. Love waves love to speed along and are the fastest surface waves. They move horizontally across the ground, much like a snake slithers back and forth. Rayleigh waves are slower than love waves, but are often much larger. These waves roll up and down like S waves, but since they do so on the surface, they produce most of the shaking that is felt during an earthquake.